So I'm going to talk about electron heating in a radiation pressure acceleration with circularly polarized laser. So this is joint work with me, one of our MSc student Krishnadev and Srinivas Krishnagopal from BARC. So let's just briefly review what is radiation pressure acceleration. So when you use thin target, which is irradiated by an intense laser, it so happens that it's a laser. If the laser quantum-motive force is strong enough, you can actually drive this entire target. So the detailed mechanics is basically you have a laser quantum-motive force which pushes the electrons first, and then that forms the electron compressed layer, but the ions are initially just not responding to the laser quantum-motive force. But because of the separation of electron and ions, you set up a large electric field that drives the ions, and then basically this is light cell like a mechanism where electrons are pushed slightly and then electric field is set and then ions are moving. So obviously you need a optimal thickness for the target, which is given by, which depends upon the laser A naught and then the ratio of density of the target with the critical density and then the laser wavelength. So you effectively you get this by balancing this electric field with the laser quantum-motive force. So that defines the optimal thickness. So just to get an estimate, what should be the typical thickness? If you take E naught of the order of 10, that means roughly the intensity of 10 to the power 20 watts per centimeter for 1 micron laser, and 100 times critical target, which is close to the solid density target. Your L optimal comes out to be about 30 nanometers. So you need a very thin target to actually drive this kind of acceleration. But the advantage of that is it can potentially lead to a monoenergetic ion beam. Also, it has a potential to boost the efficiency of acceleration because essentially you are driving the whole target, at least in the ideal condition. So the efficiency of acceleration could be higher in radiation pressure as against the other forms of laser plasma acceleration schemes. So the idea is, since the electrons and ions are going to move together, the controlling the electron heating is very crucial for the for minimizing the energy spread. Because if the electrons are heated, then the electrons are going to run away, and then that's basically the ions are going to follow them, and then the the spread in electron energy is actually going to lead to the spread in ion energy. So typically it is, so how do you manage the electron heating? The dominant mechanism for electron heating in laser plasma, laser solid, is J cross P, because so essentially if it's a linearly polarized laser, because in that case quantum-motive force oscillates with this 2 omega frequency. So that's why it was proposed by Robinson and all. Basically it says that instead of using linearly polarized laser, you use a circularly polarized laser so that J cross P is absent, and then you have a cold electrons, and then basically electron heating is suppressed and you can actually get a monoenergetic ion beam. So that was proposed somewhere in 2008. So what we have found is, even if you use a circularly polarized laser in a two-dimensional or in a multi-dimensional case, you still have an electron heating. And so for that we ran a PIC simulation with open source code WARP with a laser A naught of the order of 60 and the target of the order of 200 nanometer. And what we did is we varied the pulse duration of the laser. So in that case, this is what we have found. So this is the electron spectrum and this is the proton spectrum. And we see that as the pulse duration is increased from 15 femtosecond to 40 femtosecond, we see that the electrons are getting hotter and hotter. And correspondingly, the ion spectrum, which is fairly narrow in the case of 15 femtosecond, is becoming broader and broader, although the maximum energy is increasing. So cutoff energy or maximum energy is increasing, but the beam quality is becoming poorer as I increase the pulse duration. So that's what motivated us to investigate what is exactly happening in terms of electron heating, because we need to understand what is happening in electron heating, only then we will be able to control it. So we looked into the detailed dynamics. So as I've told, that what is happening is in the radiation pressure, it's basically the balance of electrostatic pressure, which is set up by the charge separation, and the forward Pondermotive force. So what I have plotted here is at two different times. The top panel is the electron density. The second panel is the electrostatic pressure. That is just a longitudinal electric field, the pressure because of that. And this is the laser pressure. And then the third one is the phase space density of the electrons. This is basically for the, so my y-axis is the forward momentum, and x-axis is the transverse dimension. Whereas in this case, it's in other three cases, this is my transverse direction and this is my longitudinal direction. So in the early phases, I have more or less the flat target, with slightly, I'm seeing slight modulation starting at the front of the target, but the balance between the electrostatic pressure and the laser pressure is still fairly good. That means you can see this red line is it's where the laser is now also sitting on it, and there's a fairly good balance. Because of that, there is hardly any heating at the in the electron phase space. But as the modulations increase, you see that this because of the surface modulations, the electron pressure, you see those holes happening in the electron pressure because of the modulations in that. There the balance is basically disturbed. So what was happening in this case is electrons in the compressed electron layer were coming back because of the electric field and then pushed forward by the forward Pondermotive force. So that motion was fairly regular. But in this case, once this balance is disturbed, the electrons which will come in this laser field will be Pondermotively scattered, and that leads to the localized electron heating. As you can see here, at this point, electrostatic field is not balancing the laser pressure, and then that is leading to the localized electron jets or in the energy space. Basically, so it's essentially leading to the localized hotspot creation at the location where this balance is disturbed. And this is even more dominant as you proceed in the acceleration. So these are the same type of plots at three different times. And as you can see, at the intermediate stage, you have this localized heating. But what happens is once the electrons are heated, they are sort of they will start running from the. I mean, they have a randomized motion, so they can run in different directions. And because of that, laser can puncture through this, can actually move through this. So that leads to the idea of self-induced transparency. So essentially, you have electron heating that's actually leading to in the later stages, the laser is actually going through this. So that leads to the idea of self-induced transparency. And then you can see here in the later stage, you really have this large finger-like structures which you typically see in the nonlinear stage of the Ramanujan instability, and then the electron and the laser is actually more or less filamented and fitting into these finger-like structures there. And then the electrons are essentially observed in these structures where there is a dominant Pondermotive scattering because of this, because of the formation of these structures. So this overall summarizes what is typically happening in this kind of acceleration, where you start producing these surface or density modulations. It could be a initial seed Radi-Taylor-like instability or some other instability that's I'm still not 100% sure. It's a picture is as simple as pure hydrodynamic Radi-Taylor instability, because as you can see, there is a huge plasma response also playing role there. But then with these modulations, you start electron heating, and then electron heating leads to the self-induced transparency. But as the self-induced transparency that means as the electron propagates further, it leads to more enhanced electron heating as well as the growth of the modulation. So this is more of the complete positive feedback mechanism that is going on in this detailed simulations that we see. So the next question is then, this is what it is, then is there any way to, you can actually play around with this kind of a self-induced transparency, because that's what leading to this heating and the spread in the ion. So one possibility that we sort of looked into is, well, the electron, while this thing is accelerated, you reach certain stage where you get into this self-induced transparency phase. So easiest way to do is you put a thick target back at some distance away from this thin target. So you can get an acceleration up to this distance d0, and then the laser and this target hits the thick target, and then the laser gets reflected off. So then you just basically suppress this phase of self-induced transparency. So this is what we did. So in a PIC simulation, this thin foil was separated by a thick foil, and then you have a laser coming in. And in that case, what we see is, as you change so this blue plot is basically the plot of single foil, where you have full self-induced transparency, electrons are heated strongly, and a broad spectrum in protons. But as you change the distance, you can see that the electrons are getting colder, and the ion spectrum again is becoming a monoenergetic. So you can suppress by this kind of a simple target design. It's possible to suppress the self-induced transparency, because in many cases, it may not be possible to change the pulse duration. I mean, laser systems have the finite pulse duration, and especially big lasers, it may not be possible to, if I say, instead of give me 45 femtosecond to go to 15 femtosecond, it may not be possible. Then we may have to look for alternative ways to sort of design the targets so that you can reduce this phase of self-induced transparency and sort of produce the monoenergetic protons. So I just want to present some of the preliminary results of this transverse instability. So this is what we have done with one of our MSc student, Krishnadev. So what we have done is, you can see at different stages these transverse modulations are developing. So first thing that we could do is to look into the Fourier transform and what is the K spectrum for these modulations. So these are at different times. So what we have done is we have longitudinally averaged the density, and then the transverse profile of that quantity, which is the longitudinally average, is plotted here. So you can clearly see modulations in the transverse direction in this. And then we have taken Fourier transform of it, and then we can analyze as a function of time how this Fourier spectrum is varying. So as you can see, at the early time steps, most of the dominant modes are in high K. That means low wavelength. That is expected from a typical Rayleigh-Taylor picture, because the growth rate goes as square root of K, so you should expect high Ks should grow faster. But as the time progresses, you can see that you are going to we are proceeding in the acceleration, this high K is going to a low K, and then when in the saturation stage, we see that the wavelength is around 0.7 lambda naught, which is of the order of laser wavelength. So that means either this could be a nonlinear stage of the RT instability, where people use that bubble rise model, and then you can show that you have a finite modulations, or there is some more kinetic effects, as we can see from the electron heating, are playing their role, but we need to investigate it further. So this is my conclusion. So we have investigated the electron heating mechanism in this. Shorter pulses are better, but you may not always get them. So it's better to look for a different target design, so that you could, even if you have to work with longer pulses, you don't hit that self-induced transparency phase. And we want to investigate more this transverse instability.
Thank you very much. I think it's a very timely topic, and this one is open for question. Yes.
You talked about this Rayleigh-Taylor instability, and have you looked into the growth rate of the Rayleigh-Taylor instability as for a hybrid target, like target mixed with heavy ions or so?
For these calculations, I have not looked into the mixed targets. This is purely proton that I have looked into.
Okay,
That's one thing I
this
want
is one thing, and second is, have you looked into the growth rate of relative instability with A naught of the laser?
So first of all, I'm not 100% sure whether it's pure Rayleigh-Taylor instability.
Okay.
As we can see that because Rayleigh-Taylor is considered to be hydrodynamic, when you do you solve it at the interface, and it's mainly the interface. You see that whereas we can see that here we have a huge density modulations. So one possibility, as Professor Trines was saying, that you have a density modulations that can give response to the laser, and then that can lead to a modulation, the transverse filamentation like thing, and then that can increase that can puncture these holes. So I think there is more to, although I don't have a very clear quantitative answer, there's more to it than a pure Rayleigh-Taylor.
One feeling that I have is that if it's Rayleigh-Taylor, I think the growth rate can be suppressed by mixing the target with a slightly.
Yeah, I know that there's some work in that direction.
Very nice talk. Is there an optimum separation between these two foils, depending on the pulse length of the laser that you're using, or?
So for these simulations, what I've done is I took the worst case, that is the longest pulse duration, which was giving me the broad spectrum, and tried to optimize the target. I mean the separation. So it's a balance of the energy that you can get and the spread. So if I put my target very close, then obviously I don't have any heating, but I don't have any acceleration as well. No, it's not about leading or the trailing edge. Basically, yeah, I mean, because at least in my case, I have a large A naught, I start accelerating very soon. But what happens is, if I just keep on accelerating, then at some point, the surface modulations are strong enough that laser actually goes through it.
Yeah.
So before that, I want to put other target that the whole laser is reflected. Yeah, that's right. Yeah, that's right. Yeah, that's right. Yeah.
Okay. Okay. Go ahead.
In ICF, they use, well, the ablation, the scale length of the ablation front is helpful for suppressing Rayleigh-Taylor growth. Have you considered maybe having a target comprised of two different densities or something like that to sort of create a similar setup?
Yeah, I think that's a valid point. So we are looking into that. So basically, alternate target designs for the Rayleigh-Taylor for RPA, because right now what we are doing is perhaps mostly the single target with that nanometer thickness. But you may need so that's the main point that I want to emphasize here. So different schemes can be explored.
Okay, let's thank the speaker again.